Recording.
Okay, so welcome to this master thesis defense. Our candidate today is Jay Ashworth. And this is a master defense, so it's an official presentation. Jay will present for 30 minutes approximately, followed by questions from the committee first and then the participants in this presentation. After that, we will stop the recording. This meeting is recorded, by the way, and we will stop the recording and people will leave the room and the committee will deliberate about Jay performance. And we start with that. So Jay.
Thank you, Dr. Taufer. So I'll go ahead and get started.
Mm-hmm.
Thank you everyone for coming in person and online today. Like Dr. Taufer said, my name is Jay Ashworth, and today I'm going to be presenting my thesis, Bridging HPC Data Gaps, Novel Tools for GPU Resource Monitoring and Scheduling Emulation. Before I get started today, I want to give a huge shout out and thank you to my advisor, Michela Taufer, and my committee members, Catherine Schumann and Jack Marquez, for being here today and taking the time out of their day. I also want to give a big thank you to my collaborators. First at the Pittsburgh Supercomputing Center, Julian and Paula, and also at Lawrence Livermore, Tapasia, Daniel, Mark, Olga, Stephanie, Dewi, Jim, and Tom. And finally, I want to give a thank you to the members of GC Lab that have helped me out a lot, Ian, Nigel, Paula, and Michael. Additionally, before I get started, I want to let you know that the work presented in this thesis has been used in 2 peer-reviewed posters. The first one I presented in November at the SC24 conference, and the second one is we've submitted for HPDC 2025, and it's currently under review. If successful, I will be presenting that in July. So let's get started.
And I think we have to give up there.
All right. So today in HPC, El Capitan and other exascale systems are pushing the boundaries of what's possible computationally. But the complexity of these systems makes them difficult to manage because the scale of the resources, with El Capitan, for example, reaching 1.742 exaflops on the top 500, and also the unique configurations of these complex systems, with accelerators like GPUs becoming very common, and novel resources like rabbit nodes on El Capitan. With that complexity, modern schedulers are becoming unable to fully utilize systems because of some issues like user job misconfigurations and inefficient scheduling policies. So to further illustrate those issues, first I want to talk about, it's not updating on the screen. There it goes, sorry. First I want to show you this first issue of users contributing to system underutilization. As you can see on the left, this is an example of a real job that we encountered during our study, where a user requested 4 GPUs for their job, but they only used a single one of those GPUs, whereas the other 3 GPUs just sat idle for about a day's worth of time. This is a big problem because if those GPUs are just sitting idle and the user is not aware of it, it increases the queue time for other users and can lead to expensive expansions for system administrators. Additionally, on the other side with HPC schedulers, there's a lack of awareness for certain things like IO contention. And this plot that you can see over here on the right is taken from a study on IO contention in HPC scheduling. What this plot is illustrating is that as we allocate more nodes, pictured in red, for a job, we would expect the utilization of those resources in blue to stay at a constant level, or at least somewhere near 100%. But what was actually observed is that the usage of these resources went down significantly once a certain threshold was met due to contention between nodes and IO. without the awareness of the scheduler to actually account for this, we see a huge dip in system utilization. Moving forward with those issues, we can say as the thesis statement, system utilization is impacted by user choices and scheduling policy. Monitoring tools and scheduling emulators can support efficient resource usage and thus cut costs for administrators and the time to solution for HPC users. So to target the issues that I've presented in this introduction, we make the following contributions. First, we implement a GPU resource monitoring tool to raise user awareness of common causes of underutilization, and then we visualize their usage to guide the users through improving their utilization based on those common issues. Next, targeting the issue of scheduler awareness, we develop a modern scheduling emulator with a focus on studying scheduling policy. And then we demonstrate this emulator with several key use cases. So first, I want to talk about the resource monitoring tool that we developed. And with that, I need to give a little bit of background on the existing resource monitoring tools that are available to us. In this case, we start with XC Metrics on Demand, also known as XDMod. What it is a auditing framework for NSF access systems, and it provides a detailed overview of allocation data on many access computing centers systems. Over on the right, the diagram that you see is taken directly from their website, and it is an example of the type of data that they provide to users by showing how CPU hours are distributed to individual instances within Jetstream. But one problem in XDMod is that it's unable to display per job GPU usage information due to gaps in its data ingestion methodology. But if we had this information, we would be able to identify user misconfigurations like the one I showed you earlier, which would lead to an overall higher system utilization. So to understand what's actually going wrong with XDMod, we want to take a look at how they're actually collecting data. So in XDMod, there's two different data sources that you can see in green. The first one is the job metadata. This includes information such as which CPUs are allocated to a job, as well as information like how long a job has run. Then the other data source is node resource usage, which is simply how resources were utilized over time for the system as a whole. These sources of data are collected by two agents, SLURM and Performance Copilot, and they are stored in their respective archives, which are funneled through a custom data collection layer provided by XDMod, where the data is sent off-site and displayed on the XDMod website. Now, I mentioned that the biggest problem with XDMod is that it's unable to collect the per job GPU information. And where this limitation comes in actually has to do with what information is stored in the SLURM accounting database. So what you would expect is that the SLURM accounting database would store which physical GPUs have been allocated to a specific job, but it doesn't actually do that. So to solve that issue, we introduced what we call a live GPU index parsing script. And essentially what that does is during the runtime of a job, whenever we detect that a new GPU job has been started, we will go directly to SLURM and call scontrol for that, because interestingly, scontrol in SLURM actually provides the information we're looking for. And then we save that information for later. And because we already have how the resources are used within an individual node, with this new context, we can reason about how jobs use GPUs. And then additionally, for our purposes, we store all of this data locally, and then we can do some analysis on it. So moving on, we want to analyze how these GPUs are being underutilized on our system. So what we did is we collected GPU usage information over a period of 3 weeks. This resulted in about 5,700 unique GPU jobs that we collected in our database. And among these 5,700 jobs, we took a subset of them that had an average utilization under 5% for the GPUs. And then we calculated how much of the GPU hours were wasted and divided up into 4 GPU utilization categories, and then sorted the usage in bins corresponding to what user actually wasted the time. And the shocking thing that we found, or at least shocking to us, is that out of 377 unique users during our study period, only 10 accounted for over 97% of the wasted GPU hours during the time. And while that's shocking, it's also very motivating, because with less users to correct, then it reduces our job in actually raising the utilization of the system. But to figure out how we can actually improve the problem, we wanted to take a look at user batch scripts to see if we could get any clues. So we ended up finding 3 different categories of user misconfigurations. The first one that we looked at was characterized by a low utilization among many different jobs, where these users' codes weren't effectively taking advantage of the GPUs that they had allocated. So they would just sit with 1 to 5% usage for the duration of the job. Unfortunately, because we can't look at the user's code directly, we can't say that these are always easily solvable. But that's not the case with this next group of users that we took a look at, where these users had what we call a framework misconfiguration. So in their batch script, what they would do is input the wrong value for the parameter of how many GPUs they had. So they would have allocated, say, 4, but they only put 1 into their program settings. And so as a result, the other remaining GPUs just sat idle the entire time. And since it's just changing 1 number, we said that these could be easily solvable. And then moving on to the next issue, this was very similar to the last one, where we found that users had a batch configuration oversight, where they had typos in their batch scripts that led to one of the GPUs being disabled for the duration of their jobs. So we also said that this would be easily solvable if the users knew about the issue. So altogether, taking the last 2 categories of user misconfigurations, these account for around 58% of all the wasted GPU hours during our study. And interestingly enough, as a motivating idea, all of these 58% are easily solvable issues. So to try to reason about how to tackle these easily solvable issues, we want to leverage visualization of this data to guide users through improving their utilization. And what we ended up creating is a prototype web dashboard for this visualization that is meant to provide users with a simple and easy to understand interface where they can go and identify mistakes in their batch script, like I showed before. And so users can look up their individual job or their username. If they look at their username, they'll be given a job matrix, kind of like the one in the middle, where it'll list all of the different jobs that they ran, as well as a score of utilization to allow them to quickly scan through and identify problem jobs. Then also, if they go to the specific job, they can view a detailed usage graph that shows how the resources were used. And overall, by providing this type of interface, we believe that users will be guided through fixing misconfigurations and increase overall system utilization. So with the issue of user awareness tackled, we now move on to facing the issue of scheduler awareness through our scheduling emulator. So for the scheduling emulator, we build upon the Flux Framework, which is a new and evolving resource and job management system. And through this section, I want to illustrate how Flux is continuously evolving and how we've gotten to developing our emulator with previous emulators in mind. So to start, the Flux Framework was published originally in 2014 with its initial paper. And then Flux Framework, as we know it today, exists in a repository called Flux Core. That was started in 2016 with the 0.1 version release. Now, the previous emulator that was our starting point was created around 2018. And what it provided was a way to easily study different schedulers within Flux, specifically the sched-simple scheduler, where sched-simple is just a first-come, first-served scheduler. And this happened around Flux version 0.14. Unfortunately, moving on, Flux continued to develop throughout the years, but the previous emulator stopped development around the beginning of 2020. And just 3 versions later, after it ended development, improvements to the resource management in Flux with the introduction of the resource module caused the previous emulator to no longer work. And even further, Flux continued developing with improvements to the job manager reporting. And this was once again an issue that caused the previous emulator to not work. And that brings us to today, where we introduce our advanced Flux emulator for studying state-of-the-art scheduling. So we started with Flux Core version 0.67, and we took the idea of the previous emulator and got it working with all of the modern upgrades that have been introduced into Flux. And additionally, we took it one step further and introduced support for the Fluxion scheduler, which is the kind of primary scheduler that's used on Flux. And currently, our emulator supports Flux version 0.71, and we have plans to continue upgrading it as Flux continues to evolve. So with that little bit of history, I want to talk to you about how Flux works through its core components. So to start, where a user may start to interact with Flux is in the user space. What they'll typically do is input some sort of command. In this case, we have Flux run there at the top. What this type of command will do is just simply submit a job into Flux through the Flux Python API. And at that point, Flux will be in control of the job. And so the job will go into the Flux instance, which is simply an environment to operate Flux's components. And the first component that you will encounter is known as the Flux broker. So what a Flux broker is it's kind of the foundational component of Flux, and its primary job is to communicate with other brokers, which doesn't sound like a whole lot, but the brokers are also meant to be expandable through the use of broker modules. And these are the services that make Flux very useful. And they include services like job management, resource management, and job execution and scheduling. The next thing that you'll notice with the brokers is that there's kind of a difference between, we've got one that's the leader broker, and then we've got smaller ones down below. And what this is saying is that we have this other component called the tree-based overlay network, or the T-bone. And what this does is it organizes our brokers into a hierarchical tree structure with what is known as a leader broker at the top. And since brokers are typically each deployed on a single node, the leader broker at the top will take care of specific tasks like scheduling, for example, and resource management, whereas the lower level brokers will just mainly be used to execute jobs and report information back up to the leader broker. And the final component in this diagram is the key value store, also known as the KVS. What the KVS is essentially a cache for brokers and broker modules, where if they want to store some sort of information for later and share it with other broker modules, they can do so. An example of something that's stored in the KVS is the resource configuration for the system. And that wraps up the components in Flux. So now I want to show you a picture of the components that are used in Flux Emulator. As you see, there's a lot of similarities, and that's because the Flux Emulator actually reuses all of the components of Flux, with one key difference, that the Flux Emulator skips the execution of jobs, and as a result, we actually don't need the extra resources that are represented by the lower level brokers. So whether they're there or not, we don't actually make use of them. So now that I've explained the key components of Flux, I want to go through the parallel job life cycles of Flux and the Flux Emulator, so that maybe you can understand how the Flux Emulator builds upon Flux. This process can be divided up into 6 distinct steps, and it takes advantage of the broker modules and all of the Flux components that I discussed previously. All right, so with the first step of the Flux job lifecycle, we start with initialization. In Flux, the initialization step happens whenever you first turn on Flux, whereas in the emulator, it's launched within Flux, so it actually happens whenever you launch the emulator command. So with initialization in both cases, we need some sort of configuration describing the resources that we're going to have access to. In Flux, this configuration comes from the system, whereas in the emulator, it actually is provided by the user instead of the system. And then in regular Flux, the resource module will ingest this configuration file and store it in the key value store, while the resource configuration in the emulator is directly put into the KVS. Because of this difference, we have to restart the resource module and the scheduler so that they'll actually take the new configuration. And at this point, the scheduler will acquire the resource sets from the resource module. And then finally, in the initialization step, the emulator will replace the typical job execution module with what we call SimExec, which is the key piece that allows us to skip the execution of jobs and not require resources. So moving on, we move into the submission step. This is pretty simple. Jobs are submitted by the Flux user command. In Flux, this is Flux run, and the emulator, this is Flux emulator. And then our jobs are taken into Flux. Within Flux, in this case, we're dealing with a single job, but in the emulator, because we're taking in resources from a list of historical job traces, we're taking jobs from a list of historical job traces, we're dealing with multiple jobs. Next, we move to the validation step, where the job manager will validate the jobs that have just been input. And after the jobs are validated, it'll send a scheduling request to the scheduler. And it also blocks the emulator at this step. So once we move to scheduling, the jobs will be scheduled on their applicable resources within Flux, but because the Flux emulator doesn't have resources, we schedule it on the fake resources. And whenever all of our jobs that can be scheduled at the time are done scheduling, the scheduler will let the job manager know. And in the emulator, the job manager will unblock the emulator, and we can move into the execution of jobs. So in Flux, normally your program will just be executed by the job exec module, whereas on the emulator, the SimExec module handles that. And as I mentioned, there's no system resources on the emulator. So What the SimExec module does instead is just skip time to what would be the end of the job. And then once the jobs are finished, the finish and release signals get sent by the applicable exec module to the job manager. And as we move on to the completion of the job, the resources get released by the scheduler for future jobs to be able to use. And if we have any jobs remaining from our list of job traces in the emulator, those will go back to step 4, which is the scheduling step. And finally, at the end of the entire process, in Flux, the user will be returned the result of their job, whether that be an exit code or standard out. But in the Flux emulator, the user will be returned instead statistics about what happened while executing the list of job traces in terms of the makespan and the system utilization. So now that I've detailed how the Flux emulator works, we want to demonstrate its use through some interesting use cases. So to be able to analyze how scheduling works in any system, we need a set of jobs to start with. So what we did is we took this double Gaussian distribution, and alongside it, or along the distribution, we plotted individual points that represent 100 different jobs to be used in our data set, where the y-axis in this case represented how much resources in terms of nodes that a job would be given. So on the leftmost peak, that job was given 100 different nodes, and on the rightmost peak, that job was given 60 nodes, for example. And by varying the resource requirements in this way, but keeping the time to execute each job the same, we're able to challenge the system scheduler and also provide explainable results while changing our scheduling policies. So with that list of jobs in hand, we ask ourselves two important research questions. First, does the Flux emulator accurately mimic Flux on a real system like Tuolumne, which is the system that we use to run these tests? And then also, does the Flux emulator introduce overhead into the scheduler? Because if we're introducing a bunch of overhead, then it defeats the purpose of what we're doing in the first place. So first and foremost, we ran our list of jobs on Tuolumne and through the Flux emulator using a first come, first served scheduling policy. And as you can see in the plot, all of the jobs in first come, first serve are executed in the order that they're submitted. So you can kind of see our double Gaussian distribution playing out there. And the important thing to note is that the execution of these jobs, the order that they were executed in, was exactly the same between Tuolumne and the emulator. While there was a slight difference in makespan by about 13 seconds between Tuolumne and the emulator, we attribute that to real-world factors like the prologue and epilogue scripts that are not able to be replicated on the emulator, as well as minor abstractions that the emulator makes in terms of the timing for job starts and conclusions. Then also the other very exciting part of these results is that we've essentially reduced the time to see the results of these scheduling policies from 4.2 hours on the real system to around 10 seconds on the Flux emulator. So now we try to challenge our scheduler through the use of conservative backfilling, a more complicated scheduling policy that tries to squeeze in jobs out of order to be able to allow for more efficient utilization of resources. So in green pictured are the jobs that were backfilled in our study. And as you can see, the execution order between Tuolumne and the emulator was very similar, with a single job right here in the emulator being scheduled a little bit differently on Tuolumne, causing a slight variation in the scheduling order. But overall, the results is very, very similar. And we see that by introducing the more complex scheduling policy, we're able to significantly increase the decrease the make span by about almost an hour, and significantly increase system utilization, while doing so, once again, in a fraction of the time, with 10 seconds being spent to get this result on the emulator, whereas on Tuolumne it took about 3.5 hours. So we can say that the Flux Emulator accurately mimics scheduling on a real system in a much shorter time than is needed normally. So now we want to look into the overhead of the Flux Emulator on schedulers. So what we did for this is, inside of Flux, we submitted 1,000 and 10,000 test jobs with a length of 0.1 seconds. We performed these tests on Tuolumne, and we were comparing Fluxion versus Fluxion with modifications that were made to support the study of Fluxion for the Flux Emulator. That's denoted by Fluxion plus the emulator. And we measured the throughput of Flux in completing these jobs, which is heavily influenced by the performance of Fluxion. And as you can see in the results, the throughput between Fluxion and Fluxion with the emulator was very similar. So we think that we see that the Flux Emulator does not introduce noticeable overhead into Fluxion. So with all of these contributions in place, I just want to summarize what I've talked about today. So first, what we did is we targeted the issue of user awareness in HPC through our resource monitoring tool to determine common causes of underutilization among users. And then using the data collected with this tool, we visualized and analyzed this data to guide users through improving their utilization. Next, to target the issue of scheduler awareness at HPC, we developed a scheduling emulator through our Flux Emulator to be able to study scheduling policy within Fluxion. And then finally, we demonstrated the use of this emulator through several key use cases, showing a decrease in makespan for varying scheduling policies without adding additional overhead. So we've learned that our work enables the identification of easily solvable user configurations that amount to 58% of all GPU waste. By correcting these issues, we're able to increase system utilization. And then with our Flux Emulator, we see that our work enables a reduction in time to assess scheduling policy from around 4.5 hours down to 10 seconds, contributing to the further advancement of scheduling policy, which will eventually increase system utilization when those are implemented. So as far as future work, what we're excited to be working on is with the resource monitoring tool, we want to evaluate the effectiveness of it on increasing actual GPU utilization on the system. And then finally, with the Flux Emulator, we want to investigate Flux's capabilities in scheduling an entire data center through the Flux Emulator. So with that said, I want to open up the floor to the committee to ask questions, and then once they're done, you can open it up to everybody else.
Thank you, Jay. Thank you.